Welcome. We will continue on with our discussions of the Morris-Lecar equations and in the phase plane, that is with the phase plane analysis, the tools that we are learning about. We ended the last week's discussions with an example of the sensitivity to initial conditions, which is one of the behaviors of nonlinear systems that you wouldn't see in a linear system. We showed that there is a threshold like behavior in the Morris-Lecar equations at a particular voltage, that is if we start the system to the left of that particular voltage and to the right of that particular voltage, we will get two very different kinds of behavior. On the right, that is with a voltage above that value, that is above the threshold, we get spikes, and below that value, which is below the threshold, we do not get spikes. In both cases, the system ultimately moves in the phase plane and ends at the equilibrium point, that is its resting membrane potential. So, in that case, we were starting the system somehow by moving the initial value of the voltage to a higher value by perturbing the system from the equilibrium point to a higher voltage value with the W at the same point. We can actually achieve that with a current impulse, which is a different discussion, and another way of stimulating the system that we have been drawing before is by using a current injection, that is a current that will keep on going for a period of time. So, let us say this is 0 current, this is time, and this has some particular value I naught. So, in this particular case, when I naught is approximately 95 microamp per centimeter square. So, I must say that these kind of numerical values that I am not pulling out of thin air. These are actually based on simulations which you will be provided to study. So, and the units of these are also there is a discussion that you should have had beforehand about the units of this kind of systems of equations during the introduction to simulation of these systems. So, when we have this kind of a current, this amount of current, how do we understand the behavior of the system? Let us say this is V and this is W. So, here time, so let us say it is, if this is time 0, then I external is now becoming I 0 for a period of time, as long as we want to simulate it, let us say. So, that means if we have our nullines, let us say our V nullline was like this and our W nullline as drawn earlier is somewhat like this. So, this is our W nullline, our V nullline. Remember, this is the original system that we had. Now, we have an external current that is I 0, a fixed current, which means that now I external needs to be incorporated in the system. And would it make any changes in whatever we have so far in the phase plane? Indeed, it will, because if you remember that our V nullline or W nullline is V nullline is C dV dt equals I external minus G calcium M infinity V minus E calcium minus GK W V minus EK minus G leak V minus E leak. So, now we have our dV dt equals 0, and now if we get the W values at the V null sorry, that is by replacing this dV dt by 0 and equating the rest to 0, we will see this W null is turning out to be I external minus the G calcium term with M infinity V minus E calcium minus G leak V minus E leak divided by our GK bar V minus EK. So, earlier this I external was 0. So, that makes a difference in the null line, and so now the equilibrium point is not at 0 at the V rest that we had before, it has moved away from there. Would anything be happening to our W null line? There is no I external in the W null line. The W null line was simply that WNC value, W null line values is W infinity V. Then the W infinity V did not have any I external there. So, the V null line remains the same and I external is positive. So, which simply means that this will be shifting upwards, this entire V null line will be shifting upwards. So, it will shift up to some point here. So, it will shift upwards in this manner, and the equilibrium point which was here has moved to this new point which is marked in cyan, let us say. So, the equilibrium point is changed. So, let us draw this new phase plane. Let us draw this new phase plane with the new null lines V and W, and let us say that the V null line is like this and the W null line is going like this. So, this is our new equilibrium point. And the interesting thing is that under these conditions, that is this I external equals I naught, which specifically let us say 95 microamp per centimeter square, and the system if is just outside this equilibrium point, what it would do is that it would start to move around it couple of times, and then it would move in this direction, and then it would move in this direction and keep on moving along the same trajectory all along. Which means if we look at the behavior of the system with time. So, this is the solution of the system with I 0 equals 95 and the system being started just around the equilibrium point, very close by. Remember, if we start exactly at the equilibrium point, it is going to stay there forever. Theoretically, it has to. And if when we do this for simulations, we simply start the V and W value slightly off the equilibrium point, just a tiny little bit, and then we see this kind of trajectory. So, there is a spiraling out of the equilibrium point, and then it starts to move along the same sort of trajectory along with time. So, the Vt t, which is the solution here, can be plotted, and it will turn out to be. So, let us say this is the particular v value, this is time. So, this is the v of the equilibrium point. So, if you start here, what we are seeing is sort of a movement in v like so, and then all of a sudden it bursts into large oscillations. Since it will repeat the same trajectory, it is oscillating. So, again this kind of, so these all these curves, all these oscillating trajectories are going to be identical to each other in the sense that they are repeating the same curve all along. So, this kind of behavior is what we call a limit cycle that shows oscillations. So, in linear systems, we would never see this behavior, in the sense that now let us say if I start the system here, then also it will, if in a, let us do it in a different color. Then also it will end up going on to this same trajectory and start to go into oscillations. If we start the system from outside this particular point, even then the system will go and evolve to join that same limit cycle. So, nowhere where you start in this phase plane actually within the limits of the possible v and w values, we will end up on that same trajectory all the time, which is that limit cycle. So, this means that in spite of changes in the initial value, in fact, very large changes in the initial value, there is no change in the final oscillating behavior of the system. In other words, in a linear system, if we have to see oscillations, then it becomes the size of the oscillations would become proportional to the input size. In this case, it is going to converge onto the same sized oscillations and the same oscillations throughout. So, this is another typical behavior of nonlinear systems, or another different kind of behavior of nonlinear systems, which make these systems so interesting to study. And we will see that this kind of limit cycle behavior does exist in neurons, where we have a small fluctuation that can then go into oscillations if we have a background current for a while. Now, so both the things that we have seen so far, they actually we presented it in a manner such that as if with simulations we came upon those phenomena like the limit cycle here or the threshold kind of behavior. It is as if we said that if we keep on increasing v, a point will come when all of a sudden there will be action potentials after a particular value. And here also it is simply that okay, let us start near the equilibrium point and then try out other places and see that okay, that is going into that trajectory all the time on the limit cycle. So, actually we can in fact have make predictions about these systems, whether they will have a limit cycle or not, or at least based on different conditions can predict whether they will necessarily have a limit cycle or not, or otherwise, or if there is going to be threshold behavior or not, and so on. That can be done based on simply looking at the equilibrium points, the properties of the equilibrium points. So, as you may notice, we did this, we did this earlier when the equilibrium point was here, and if you remember, if we started here, the system would go back and come back into the equilibrium point. In this case, it is actually going away from the equilibrium point and going on to this trajectory here in the on the limit cycle. So, how do we know a priori beforehand, given the system without simulating, whether the system is going to go away from that equilibrium point or whether the system is going to come back into the equilibrium point? So, for these very ideas, it is formalized by looking at the stability of the equilibrium points. So, in we can compute the or we can determine the stability of the equilibrium point by linearizing the system close to the equilibrium point. In other words, if we consider the entire system and then look at a very small neighborhood around the equilibrium point in the phase plane, then we can change the system of differential equations into or rather the dv dt and dw dt into linear functions. And with those linear functions, we can determine whether the equilibrium point is stable or unstable or something else, which we are going to discuss in a little bit. So, if the system is attractive in nature, if the equilibrium point is attractive in nature, that is how it was in the earlier case where there was no I external was 0, we found that the trajectories went and ended up at the equilibrium point. So, those kind of equilibrium points are the stable equilibrium points, that is they attract the trajectories to come and stay there. And the kind of equilibrium point that we can talk about here is unstable equilibrium points. So, in order to look at the stability and linearize the system, we have to take into account a little bit of mathematical treatment around of the equations. We will try to understand the stability of the equilibrium points based on linearization around a small neighborhood around the equilibrium point. Let us say that for any system, let us first consider an n dimensional system like this, where we have our vector variable x dot, which is a function of the vector x, which can be, let us say, represented. Let us say x, the vector x is given by the elements x1, the variable x1, x2 up to xn, and the derivative, and these are the derivatives of that, and f(x) is basically going to be f1 function of the elements x1 up to xn, and this is f2 x1 up to xn, this is fn x1 up to xn. So, if we were to linearize the system, we have to replace this by a polynomial and consider only the up to the first order term. So, if we use the Taylor series expansion, then with f1 x1 up to xn, we will see that we have the 0th order term, which is f1 at 0, or here we are evaluating it at the equilibrium point, which is, let us say, our x 0. and this x0 as a vector is x10, x20 up to xn0. So, this f1 at x0 is going to be the first term, and then plus del f1 del the entire vector, then we can sum it up with del x1 into x1 minus x10 plus del f2 del f1 del x2 x2 minus x20 and so on. So, these are the only first order terms for this n dimensional system. So, we now f1 x naught, where x naught is the equilibrium point, we know is going to be 0. f1 x naught is equal to 0, and here I am sorry, the del f1 is evaluated at x equal to x naught in each of these cases. So, this term goes to 0. So, we are only left with the derivatives or the partial derivatives of f1 with respect to x1, x2 and up to xn. Similarly, for f2, we can replace it by f2 x naught and then del f2 del x1 and so on with the multiplication of x2 minus x20 and so on. So, now again f2 x naught is also going to be 0. So, with this we can extend the idea and see that this is turning out to be x1 dot x2 dot up to xn dot is, by setting these terms to 0, we will have del f1 del x1 and this is multiplied by x1 minus x1 naught and del plus del f2 del x2 x2 minus x2 naught and so on. I will not extend these terms. Now, if we substitute x is equal to, or x as the change delta x, let us say, is x1 is x1 minus x1 naught, then our x1 dot is also simply delta x1 dot. This is simply the coordinate of the equilibrium point along x1 axis. So, these x1 minus x1 zeros, x2 minus x2 zeros can be replaced by a single variable, let us say little x, and this can be replaced similarly by the single variable little x dot for the entire vector. So, let us go one step further, that is, we have x1 dot, x2 dot up to xn dot, and now we convert the earlier functions. We can write it as simply a matrix multiplied by a vector, where we have del f1 del x1 as the first term along the first row, del f2 del x2 as the second term in the first row and so on, multiplied by the vector x1 minus x10 is the first term, x2 minus x20 is the second term and so on. So, here we will see that we can replace it with del f1 del x1 evaluated at the equilibrium point, del f1 del x2 evaluated at the equilibrium point, and then del Fn, del F1 del Xn multiplied by x1 minus x1 naught, x2 minus x2 naught up to xn minus xn naught. So, by multiplying this row with this vector, we get the term that we had written earlier, which is this sum. Similarly, for the next function, the next variable del x2 del x del f2 del x1 evaluated at x naught and del f2 del xn evaluated at x naught. So, now if if we replace x1 x by or capital X by little x, then this whole equation can simply be written by x dot equals this matrix, which is a Jacobian times x, where x is a vector, which is where x is representing deviation from the equilibrium point. That is, we had this in our case v and m in the two dimensions, and this is, let us say, the equilibrium point. Then the 0 of this x is at the equilibrium point, and x is representing any position with respect to this particular as an axis. So, it is this x1 minus x1 naught is the deviation from the equilibrium point along this axis, and x2 minus x2 naught is the deviation along the equilibrium point on this axis. So, and this matrix that we have written here is called the Jacobian matrix, and it simply is the first order derivatives, partial derivatives evaluated at the equilibrium point. So, now that we have linearized the system, so this is, as you can see, is simply a linear system where we have only first order derivatives, and we have removed all the second order terms. So, this neighborhood is such that this system has to be valid, this linearization has to be valid. So, the behavior of the system, what we will derive from this final form little x dot equals j little x must be valid only in a very tiny region around the equilibrium point. We, as soon as the system goes out of the equilibrium point or out of that neighborhood, tiny neighborhood, the system will start I mean, it will not follow this linear behavior anymore, and we will have to linearize the point again and so on. So, near the equilibrium point, the x dot equals jx, this system of equations is going to predict the behavior of the system. So, for a equation of this form equals jx, there is only there is one solution to this equation, which is if I mean it the initial conditions can be come about later. Let us say if x is made up of x1 and x2 equals j and x1 and x2, then if j has eigenvalues lambda 1 and lambda 2 and eigenvectors, corresponding eigenvectors v1 and v2, then the behavior of the system is that x xt So, this is the general solution for a two dimensional system uh, with the matrix J having eigenvalues lambda 1 and lambda 2 with eigenvectors corresponding eigenvectors v 1 and v 2. You can check yourself that this is the solution by plugging it into the x dot here and x there, and you will find that this is indeed the trajectory. So, the behavior of the system near the equilibrium point, let us say here this is x 1, this is x 2, will be determined actually now by these eigenvalues lambda 1 and lambda 2, because if we have and v 1, let us say v 1 is this direction and v 2 is in this direction. What this equation is showing is that at very close by the system will move along the eigenvector v 1 and will have an exponential trajectory e to the power lambda 1 t, and at the same time it will move along v 2, the eigenvector v 2, exponentially with e to the power lambda 2 t as the function. So, obviously, if our lambda 1 and lambda 2 are less than 0, when we say less than 0, we are already implying that lambda 1 and lambda 2 are real. Then we can see that if the system is around the equilibrium point, then because the lambda 1 and lambda 2 are negative, over time this term e to the power lambda 1 t and also e to the power lambda 2 t is going to go to 0, which means that both along v 1 and v 2 it will finally die down into the equilibrium point. So, when lambda 1 and lambda 2 are going to be less than 0, this would be a stable equilibrium point. Similarly, if lambda 1 and lambda 2 are both greater than 0, then the system is going to be an unstable equilibrium, or not the system, the equilibrium point is going to be unstable, which means that based on this solution, that over time the system is going to go diverge out in along v 1, the first eigenvector, and also along v 2, the second eigenvector, and so it is not going to come back into the equilibrium point, which would be so its behavior would be to push out the system from near the equilibrium point, because of simply the sign of the real eigenvalues in this case. And we will see that even for complex lambda 1 and lambda 2, if the real part is negative, then it will be a stable equilibrium point, but with an additional property of being a spiral, then that will be called a stable spiral. Similarly, when lambda 1 and lambda 2 are both positive, then also it will be again unstable with an additional property that it will be a unstable spiral, which means that if this is the equilibrium point and this is v 1 and this is v 2, for a stable spiral it is going to go like this and gradually end up into the equilibrium point. So, this is the final direction. And obviously, for the unstable spiral, if this is the equilibrium point and this is V1 and V2, then if we start the system near here, it will gradually move out of the equilibrium point or from the vicinity of the equilibrium point. So, remember that these are only valid only close by, but that is sufficient to predict the behavior of the trajectories that are going to come around it, close by it, and we will see that indeed with this analysis we can conclude a number of things about the system's properties and the phenomena that the system can show. So, we will stop here by next going on to another kind of equilibrium point, which is the last obvious case that is remaining, that is lambda 1 and lambda 2 being of opposite signs, that is, let us say lambda 1 is positive, lambda 2 is negative. That has a very different kind of behavior, and that is called a saddle node. So, if I can write it down, lambda 1 is less than 0, lambda 2 is greater than 0 or vice versa, then this is called a saddle node, whose properties we will be discussing in the next lecture. Thank you.